Okay, so the topic today is modular arithmetic. I want to review the theory. So this is the theory of inverses and exponents. Um, so we'll start with the statements of the basic theorems from Euler, and Wilson, and also the existence of inverses. So um, so this is problem one. Um, so I started with this statement here. Okay. So this statement I'll explain in a moment, but I think it's or the way I think of it is the fundamental lemma of modular arithmetic. It's what you use to prove all the basic theorems. So what does it say? It says I have A and N are co-prime positive integers, so it's important they need to be co-prime. You guys know what co-prime means, right? It means relatively prime, co-prime, mean the same thing. No common prime factors. So we have A and N, which are co-primes. So N will be the modulus and A is the number. Um, and the lemma is that if you take the set 0 to N minus 1 and you multiply by A, it's the set stays the same modulo N. Okay, so let's okay, simple examples. If I go mod 7, for example, and I take 0, 1, 2, 3, 4, 5, 6. And then I double everything, so times 2. So N is 7, A is 2. Then it becomes 0, 2, 4, 6. And then what? 8 is 1. So 1, 3, 5. Like this. And so it's the same set, just permuted, right? Um, so why is it true? What's the proof that this is true?
Uh, 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 there is some lemma before we prove it. We prove that a, a times 0 and a times 1, uh, like we prove if m and n are not, or l and k are not congruent to each other modulo n, then we have a, or we can prove the contrapositive.
Okay, great. So yeah, I'll write what you said and also the contrapositive. So we'll prove that if L and K are different modulo N, then AL and AK are also different modulo N, right? So this is the lemma. And okay. So what does the lemma mean? It means that when I look at this set here, after I multiply everything by A, everything is different modulo N. Yeah. Um, okay. And so the proof is, like you said, it's by contrapositive. So we show the contrapositive. And so what is contrapositive? We show that um, AL congruent to AK mod N implies L congruent to K mod N. And how do we do this? Well, it's okay. So it's kind of, we'll start with the blue. And then what will we say? This implies that AL minus AK is divisible by N. Okay. And that means
Uh,
N divides, yes?
uh, or we can prove that AM is congruent to 0 modulo n is equivalent with M is congruent to 0 modulo n. It's
I
the
see.
same thing.
Okay. Yeah, okay. So let's okay, so Karam is pointing out that this statement it's equivalent to showing that what? Okay, you can do it like this. You can say um what does this give us? This gives us A times L minus K is congruent to 0 mod n. And so what? It means n divides a times L minus k. And now what? So now we use the assumption that
A is coprime.
A, that's right. So now we need this coprime assumption, right? This is why it's important that A is coprime. Otherwise, this entire thing is false. So now that A is coprime, it tells us that n actually divides L minus k, right? Because there's no common factors between n and A. And then
or
we
we
get
can
back.
or we can prove that using visit identity.
Yes. So you were saying for this step here, yes?
Yes, to prove this application.
Okay. So good. So okay, this is a good point. Why is it true that if n divides both of these and it has no common factor with A, then it divides these? So maybe I'll make a side comment here. So yeah, you can say maybe the fundamental step in this proof is that if n divides, if n divides A times B and A comma n are coprime, then n divides B, right? This is the key step, I guess. And well, okay, there's two reasons one that this you can show this. So I don't want to go into too much detail, but okay, proof one of this claim is you can use factorization, prime factorization. So you can factor A and B, and you can see that okay, every prime factor of B has to be a prime factor of n with every prime factor of n has to be a prime factor of B with higher multiplicity, right? Okay, so that's one proof, but you're saying there's another proof by Bezout. So what does Bezout say? So Bezout says that because A and N are coprime, you can find there exists integers x and y such that ax minus ny equals 1. So that's what Bezout says, is whenever A and N are relatively prime, there's a combination you can do that gives 1, right? And then how do we finish from here, Kyle?
Maybe we suppose that that n does not divide
Does not divide B, you mean here?
yeah, I mean B.
Yeah, okay, let's see. Okay, I think I need to think about this. You can prove it from here, but wait, I don't want to focus too much on this. So I know you're right. There's a way to finish the proof from here. So I'll just say dot, dot, dot. I don't know actually how it works, right? So from here, what do? I say and divide. Okay, maybe I need to think about it. I don't know. I don't know right now actually. So okay, we can say dot, dot, dot. Maybe you can tell me for homework how you finish this proof.
Okay.
Yeah. Okay, but what was the point? So the point was we proved this. We showed that L and K are different, then AL and AK are different, modulo N. And then how does that finish this? So how do we deduce the problem from the lemma?
It means that every element in the set is unique.
Mm-hmm.
So, and there are
So
only,
in this set, yes? In this set, everyone is
yes.
unique, yes? Yes.
And so it's basically, and the options are 0 to n minus 1. So yeah,
Yeah, so it's like like Abdullah says, it's clear, right? So it means these are all different. There's n of them because it has the same size as this, and there are only n options. So it's each one happens exactly once, right? Does the argument make sense? It's a counting argument.
Yes.
Okay, yeah, so we can say it like this, maybe. We can say, okay, the map from 0 through n minus 1 to 0 through n minus 1, which is given by you send k to ak mod n, is injective. And then that's what the lemma says, is injective by lemma. And then the domain and these have the same size, so therefore bijective. Because it's a map from a set to itself. Does it make sense what I wrote here?
Yes.
Okay. Okay, so now let's see, how do we apply this lemma to all so what are we doing? We're proving 4 things with this lemma, right? So let's start with the first one. We are proving first the existence of multiplicative inverses. Okay, so let's look at that. So we want to deduce that if A and N are co-prime, so it's the same setup as before, then A has a multiplicative inverse. So what is a multiplicative inverse? It's going to be an integer B, so that when you multiply A and B, you get 1 mod n. Okay. So how do we deduce the existence of multiplicative inverse from the lemma? Maybe I should
Since we have both sets are equivalent, then there exists a number between 0 and minus 1, such that multiplied by a, it's modulo 1. Because there
Yep.
needs to exist a distinct number that is modulo 1.
Exactly, right? So what does the lemma says? One of these is congruent to 1 mod n. And that's your inverse. Right? Okay, great. And actually it shows that inverse is unique, right? There's only one. There's only one of them is congruent to 1 mod n. Okay, so we can even say it has a unique multiplicative inverse. Unique mod n, that's the uniqueness is mod n, right? Okay, great. Okay, so what's next? Next we say the next we want to prove Euler's theorem and Fermat's theorem, right? So from this, right? So I will claim that from the fundamental lemma that we proved, you can produce Euler's theorem and Fermat's theorem. So what is Euler's theorem? So again, it's the same setup. You have n is your modulus and a is your integer. And then we define phi of n, the totient function. And the totient function, probably you guys have seen it before, it counts the number of residue classes that are co-prime to n. So what is phi of 6? So for phi of 6, I write down the residue classes, mod 6, and I see which ones are co-prime to 6. So in this case, I throw out 0, 2, 3, and 4, because they share a common factor. I'm left with 1 and 5. So it means phi of 6 equals 2. Okay. So that's what phi is. And the totient theorem says that if I take A, which remember is coprime, and I raise it to the power of the totient function, I get 1 mod n. Okay, so the theorem of Euler is that A raised to the phi of n is congruent to 1 mod n if A is coprime to n. So how do we prove that from the lemma?
I think it use another lemma, but it's similar to this.
What's the
Uh,
other lemma?
the same thing, but if we have the set of all residual classes from 0 to n minus 1 that are relatively prime with n, then we multiply it by a.
Great. So we need a lemma, which is we need to modify this. The problem here is we have too many residue classes here. We just want to take the ones that are relatively prime. Okay. So let S, we can consider it as a subset of 0 through n minus 1, be the set of residue classes that are coprime.
But we don't have 0.
But 0 is not coprime. 0 is not coprime.
Yeah.
Right? So we'll say the residue classes that are coprime to n. When you say that, it throws out 0, right? Because 0 has a common factor.
I thought that S equal 0 to n minus 1.
No, this is subset.
Yeah.
So yeah, this notation, it means S is a subset. It's not all of them. And which ones is it? It's the ones that are relatively prime to n, as you said. So what is the lemma says? It says that if we look at how else? Okay, we have S, and then we also have, I'm going to call it A times S. What do I mean by A times S? Okay, maybe I need to define what that means. So
the elements of S multiplied by A.
Yes, the elements of S multiplied by A. So let me write that formally. So okay, so let's give it, that's the definition. What is AS? So AS is defined to be the set of, let's say, A times K, where K is in S. Okay, so you multiply everything in S by K, and now the lemma is that S is congruent to AS mod n. Okay, so if you take the residue classes that are coprime to n, I multiply them by A, where again it's important, A is coprime to n. So I take the coprime residue classes, I multiply them all by A, and the lemma is that it's still the same. It's still just the coprime residue classes. So the statement makes sense for everyone?
How do we know this is true? Like why isn't it
So you're asking about the proof, right?
yeah.
Okay, but the statement makes sense.
Yeah, it makes sense.
Okay. Okay, so yeah, maybe you can tell me, Abdullah, how do you prove it? Like, what was you said, how do we know, what was your concern?
So how do we know when we multiply it and take a mod n? Oh, it's always gonna say coprime and it's unique. Is that why this is true?
Yes. Yeah, so your question you're gonna ask me is how do I even know that AS is contained in S, right? How do I know that when I multiply by A, it stays coprime?
Yeah,
That's your
exactly.
Yeah, so that's the first question. So maybe we can answer. Why is that true? Why is it true that it stays coprime?
So both numbers are coprime to n.
Exactly right. So maybe we can, I don't know, write an orange or something. The point is if A is coprime to n, and b is coprime to n, then it implies that a times b is coprime to n. Because what is coprime? Coprime is just about having common factors. So if a has no common prime factors with n, and b has no common prime factors with n, a times b also has no common prime factors. Okay, so that's the first thing we have to understand, that AS is contained in S, right? And then what's next?
We show that we do the same thing that we did in problem 1. Like if we have two different elements of S, then like K is not congruent to L mod N, then we have AL is not congruent to AK mod N.
Great, so we need to use this lemma again, right? L and K are different, then AL and AK are different. So maybe this lemma is so important, I'm going to give it a name and call it lemma 0. Okay, so this is lemma 0. And the important thing is, what does it mean? Because we have lemma 0, by lemma 0, elements of AS distinct modulo. You guys cannot read this. Let me write it better. I'm saying, yeah, by lemma 0, these things in AS, they're all different mod n.
So the
Right,
coordinate
so-
of S is the same as coordinate of S.
Exactly, right. So by lemma 0, elements of AS, how we say, distinct modulo n. Okay. And then it follows, right? Because we showed AS is contained in S. The elements of AS are all distinct modulo n. And they have the same size, so they must be equal. Yeah, so it makes sense. It's
We can prove that by pigeonhole principle.
yeah, so it's pigeonhole. I mean, you can I think you can just say it, right? Like what's the thing? Like if this set is contained in here, they have the same size, they must be the same. I think it's okay, yeah. Yeah, like because there's no repeats, it shows that AS is the same size as S because there's no repeats in AS, and so they must be like once I have one set is contained in another and their size is the same, it means they're the same set. Okay. Okay, so great. So now we proved this. So this is the version of the fundamental lemma, or what I call the fundamental lemma. That's not a real name, but this is a version of the fundamental lemma for modular arithmetic, but for coprime residue classes. So from that, how do we deduce Euler's theorem?
We consider since S is congruent to AS mod N, so the product of all elements of S is the same as the product of all elements of AS modulo N.
Excellent, right? So let's let me write down what you just said. Great. So now that we've proved it, I will erase the proof. And okay, so oh no, so that one. Okay. So right, so the idea is I want to multiply the elements in both sets. Okay. So I want to take product of say K and S, of S, and of K rather. So I'll write it like this. I multiplied all the elements in S, that's what this notation means. Should be the same as multiplying all the elements in AS because they're the same set, right? Modulo n, they're the same set. So when I multiply all the elements, they're the same modulo n. Okay, but so now what? What does that tell us?
The product of all the elements in AS is A to the totient function of n times the product of elements in S.
Great. Right, so the point is this guy here, we can write it in terms of this, right? Because we can say it's the same as if we multiplied over k and s of AK, like this. And then we
Yes.
can pull all these A out, right? So we pull out all these A's and okay, so we pull out all these A's, what happens? Well, how many A's do we pull out? We pull out totient many. So this is A to the totient of n times product k and s of k, right? Because we just multiplied everything by A, so the whole product got bigger by a factor of A to the power of the size, which is the totient function. Okay, great. So this is looking very good. We have this and this are equal. How do we finish the proof?
We just subtract the product from both sides.
Subtract?
Yeah.
Oh no, it's not because you can't subtract, right? Oh, I see what you're saying. No, I understand. You're right. Yes, you're correct. You're correct. Sorry, I was thinking divide, but yes, you can also subtract. So let's do subtract. So what does it mean? Yes, you're right. So, so what does it mean? So, right. We have this, and you're saying that we can subtract. So if we subtract, what happens? We get a to the phi of n minus 1 times this product is congruent to 0 mod n. Okay,
Since
so
the product is of coprimes, it can't be 0. So
exactly right. So so now it's all right. So this is important, right?
Actually, we are using the lemma 0 here.
Are we using lemma 0? Ah, yes, we are using lemma 0 because we're saying that right, so we're using lemma 0 with this number, right? So okay, here's the important thing. Product k and s of k is coprime to n, right? Because each of the factors is coprime to n, so the whole thing is coprime to n. And then we're saying, okay, this number times something equals 0. So actually it tells us by lemma 0, a to the phi of n minus 1 is congruent to 0 mod n. You're right, it's an application of lemma 0. Does this make sense why I'm calling it lemma 0? But we're using lemma 0 with this as a. Right, we're saying if let's call this maybe x or something. We're saying if x times L is congruent to 0 mod n and x coprime, then L is congruent to 0.
Or actually, we don't have to do that. We know that we from the first statement we can deduce that the product of all elements of S is congruent to A to the totient of n times this number. So now we can deduce that a to the tuition function of n is congruent to 1.
You're saying directly from here.
Yes.
Yes, yes, right. Because why? Because
They're co-prime.
right. Okay. Yeah, because yeah, but okay, I want to make some point here, right? Like what we're really doing here in all these cases is so here we can say, okay, we have okay, let's call this number, what we called it, x. So yeah, we have what? So this thing is telling us a to the phi of n times x equals 1 times x mod n. And so again, by lemma 0, it means a to the phi of n is equal to 1. So the important thing is it's like we're dividing by x on both sides. And the reason we can do it is because it's co-prime to n. Maybe that's the so that's the point. So in particular, that's why we needed to restrict to s, to the co-prime residues. Like we could have started with we could have done something where look, we can say something like we can just start with these directly. We can say, you know, the n minus 1 factorial is congruent to a to the power n times n minus 1 factorial, something like this. But then we cannot cancel because it's not co-prime anymore. Does it make sense what I just said?
Yeah.
Okay. All right, so that was the proof of Euler's theorem. Okay, Karim, you're able to join. So Karim, if we haven't really done all that much so far, so if you have any questions, please interrupt and I can go back and explain.
No, it's fine. I'm quite familiar with these topics.
Okay, great. Okay, so now let's prove Fermat's little theorem. So this is it's just the version of Euler's theorem for prime numbers. So what does it
This
say?
problem 2 can be proved the same way.
Yes, it can. Yeah, so this one here, Fermat's little theorem. So this is the one that says what? If it's the same, but actually, okay, it can be proven in the same way because it's a special case, right? It's really the same theorem, just for n is prime. So what is it saying? So let's look at this version of it, which says that if p is prime, and a co-prime to p. Now, okay, if p is prime, what does it mean a is co-prime to p? It just means p doesn't divide a. Okay, it's the same. It's okay. Then, okay, we have a to the phi of p is congruent to 1 mod p. But what is phi of p? Okay, it's the
Minus
residue
1.
classes. It's p minus 1, right? So I look at 0, 1 through p minus 1. Which ones are co-prime to p? All of them except for 0, right? So phi of p is p minus 1. So it shows a to the p minus 1 is congruent to 1 mod p. Okay. And that's what Fermat's little theorem says. Okay. Okay. So that's what Fermat's little theorem says. It says if p doesn't divide a, then a to the p minus 1 is congruent to 1 mod p. What about this thing I wrote here? I wrote here that if you don't put any restriction on a, so even if p divides a, it's true that a to the p is congruent to a mod p. You guys see how it's equivalent?
Yeah.
Yes.
Like if p divides a, then
0.
both sides are 0. And if p doesn't divide a, I just multiply both sides by a, and that's true. Okay, so it's all actually equivalent. All right, so great. So that's Euler's theorem and Fermat's theorem. Now what's next? Next is Wilson's theorem. But yeah, okay. Next is Wilson's theorem. So yeah, okay. I was gonna do this later, but I think it's okay. We can do it now. So what is Wilson's theorem? It says I have P is prime now, and it says that if I take P minus 1 factorial, I get minus 1 mod P. So how do you prove this?
We just paired them.
Yeah, it's a standard. It's Euclid's. Euclid? No, Gauss. Gauss's pairing trick, right? So we do Gauss's pairing trick. So what does it mean when I write P minus 1 factorial? It means I write 1 times 2 all the way times P minus 1. Now, I'll make a comment, what is this, what are these numbers I'm multiplying? It's the same as this set S from before, right? We had this set S, like this. When n is prime, so when n is P, S is just 1 through P minus 1. So it's, I'm determining what this factor is in the case that n is prime. So yeah, so let's do that. Right, so yeah, the comment I was making, this is equal to the product of K and S of K. And your suggestion is to pair them. So, and you pair them how? I pair each element with its multiplicative inverse. Okay. Okay, but then how come I don't get congruent to 1 mod P? Right, I pair them, I pair each one with the multiplicative inverse, so I just get 1 times 1 times 1. Why doesn't it work? Why am I not getting 1 mod P? Why is it minus 1?
Because their primes are odd, except 2.
Why does that matter?
One of them is not going to be paired. No?
No, but if primes are odd, right? Then I have P minus 1 is even. So I have an even
Oh,
number of numbers. There's an even collection of numbers here, so it's okay.
because one is the multiplicative inverse of 1, no?
Right, so 1 is that, okay, 1 times 1. So okay, yeah, so multiplicative, maybe we can write it like this. Usually we write to the power minus 1. That's the notation we use. So we say 1 inverse is 1 mod P, right? So the multiplicative inverse of 1 is just 1. Okay, so now that's weird, right? Because I have what? Here I have even many terms. One of them paired to itself. Right? Does it make sense? One paired with itself. I have left an odd number of things. You guys see the problem I'm facing? I have one pairs with itself, and then I have left an odd number of things. So how did that work? So
We just have to consider x squared is congruent to 1 modulo P. And
right.
solving the equation, we get it's 1 and minus.
Before we solve, let me just illustrate the problem that we're facing, right? So you're right. So what you're telling me is that there are other numbers that get paired with themselves. So let's just see this problem in action. So let's do mod 5. So P equals 5. So what are the classes? They're 1, 2, 3, and 4. And how do they get paired? So 1 gets paired with itself. And what else? So what does 2 get paired with? What's the multiplicative inverse of 2?
3.
It's 3, right? Okay, yeah. So I write 2, 4, 6, 8. and the one that's 1 is 6, right? So it's just gets paired with itself. So 2 and 6. And that means 4 must get paired with itself, right? And it's true. 4 times 4 is 16, which is 1 mod 5. So we see there are 2 numbers that get paired with themselves. And does anyone have a conjecture okay, maybe I'll say, like, why did 4 get paired with itself? The reason is because 4 is actually -1 mod 5. And you'll see -1 is its own multiplicative inverse. Okay. So the conjecture, or we can check it, is that 1 and -1 get paired with themselves, so they're their own multiplicative inverse, and everything else is different from its multiplicative inverse. Okay, so let me write down what I just said. So this is a lemma. We'll say x is congruent to x inverse mod p, so p is prime, if and only if x is either 1 or -1 mod p. Everything else is different from the inverse. Right. So let's prove this. Yeah, so let's prove this. The proof. So one direction is clear, right? So if x is congruent to 1, then okay, well, 1 times 1 is congruent to 1 mod p, so it's its own inverse. If x is congruent to -1, then we take -1 times -1 is 1 mod p, so it will be its own inverse. So what about the other direction? Suppose x is congruent to x inverse mod p. How do we show that x is either 1 or -1?
We square it.
So when you say you square it, you mean you multiply both sides by x, so you get square on the other side, right? Because what we start with is this, right? Do you understand what I mean?
Yeah, but don't we have that if A is congruent to B mod M, then A squared is congruent to B squared mod M also?
It's true, but then what does it mean? It tells us x squared is congruent to x, the x inverse squared mod p. Yes? Like Adam, if we just square both sides, we get this, right?
Yeah, but also when you multiply by x, we get x squared is congruent to 1.
Yeah, exactly. So what we want to do is we want to multiply by x, right? So if we multiply by x, okay, and we can do that, then we get x squared is congruent to x times x inverse, which by definition is 1. Okay, so the x squared is 1 mod p, and then what do we do? Okay, so then, yeah, there's many things we can do. We can subtract 1. And the x squared minus 1 is 0 mod p. Okay, so from here, what do we do? How do we solve this?
We vector it.
Yeah, so you can factor it, and then we have x minus 1 times x plus 1 is congruent to 0 mod p. But are we done? Can we just say x is 1 or minus 1? Is it
we know that x is less than p, so that's why we can not just congruent but equal.
well, so what does it mean? I mean, if x is less than p,
We
Um,
can just say, since it's congruent to 0, we can just say P divides x minus 1 times x plus 1. So it either divides x minus 1 or x plus 1. And we get our solutions.
yeah, so okay, good. So yeah, we should use the fact that P is prime. So let me actually make a comment, Abdullah. So it's not, because we're dealing with like modular arithmetic, x being less than P is not that I don't know if it'll help us. So let me give an example.
But I
Suppose,
mean in our set, initial set, 1 through P minus 1.
yeah, it's true. We can pick, yes, it's true. X can be less than P, but that like yeah, why did that help us though?
Since we know that x is less than P, we know it has to be equal and not just congruent. No?
But why? Because x squared minus 1 could be up to P squared minus 1. There's a lot of numbers from 0 to P squared minus 1 that are 0 mod P.
Okay.
You see, right? Yeah, so and yeah, like maybe just to drive the point home, like it's important here that we have to understand we're doing something about P being prime, because if it's not, let's take 6 for example. Mod 6, and let's take the number.
We use a prime probability.
Sorry? Okay, let me I need to give an example here. So well, maybe 6 was not a good example. Maybe I should do something different. So maybe I will do 10. No, 10 is bad. 15, mod 15. Okay, so I will do mod 15. And I will take 4. Okay, x is 4. X is 4, then x minus 1 times x plus 1 is what? It's 3 times 5, which is 0 mod 15. You see, so it's you really need a P is prime here. You guys see the point of this example?
3 times
Yeah.
5 is not 0 mod 6.
15. I picked 15, not 6.
Yeah.
Yeah, sorry. 6
Okay.
doesn't 6 actually it doesn't work. There's no counterexample. But for 15, you see there's a problem, right? So we really need this P to be prime. Okay, so yeah, but okay, how do we use that P as prime? Well, we say, look, we have
We
since
use
we
the prime
factored it, we
probability.
know. Yes, the prime property. So because P divides the product, it divides one of them. Okay, so it means either P divides x minus 1 or P divides x plus 1. And then we get the conclusion that either x is 1 or x is minus 1 mod P. Okay. Great. So yeah, so what was the point? We were able to prove that the only number mod P that is its own inverse, its own multiplicative inverse, are 1 and minus 1. Okay. So why it helps us because now when we write this product 1, 2, all the way P minus 1, we multiply all these numbers in S, everything can be paired with its inverse except 1 and minus 1. So this will be equal to, we'll get 1. How many times? We'll get 1. So how many pairs do we have? We'll have P minus 1 minus 2 over 2, right? So we'll get P minus 3 over 2 of 1. And then we'll get times 1 times minus 1, which is just minus 1 mod P. Yeah, so it makes sense, the proof of Wilson's theorem.
Yes.
So I didn't put this on the homework, but now I think I should. So I'll add it later. But yeah, so this Wilson's theorem is about multiplying the numbers in S when n is prime. But what if I just, I just ask, for any n, we can take any n, right? And right, so we can take any n, and yeah, we have the set S, right? And I can ask, what is this product? What is the product of K and S mod n? What does it equal? Does it equal -1, for example? Okay. And so now you'll notice I can still pair because the things in S are co-prime, right? So they have an inverse, so I can still pair things with its inverse, but it's not that easy to understand which numbers get paired with themselves. So it's a little bit subtle. So I'll leave it as homework to figure out what this is. There's a good answer. It's a very nice answer, and you can figure it out. And yeah, so I'll give it as homework. Does anyone know the answer off the top? Like, has anyone maybe seen the problem before? Okay, so it's a good problem. It's good homework. So okay.
Wait, which one?
So the problem of determining this product. You understand the problem?
Oh, okay.
Yeah, so I take all the residues co-prime to n, and I multiply them, and I see what I get mod n. Okay. So great. So now let's talk about order. Okay. So this is related to Fermat's theorem and Euler's theorem. So the order of an integer modulo n. So we have the same setup. We take n as our modulus and a is a co-prime integer, co-prime to n. And we define something called the order. So it's the order of a modulo n. And what does it mean? It means, well, okay, so we know a to the phi of n is congruent to 1 mod n. This is Euler's theorem. But we don't know if phi of n is the smallest exponent, which makes this true. There could be something smaller. And that's what we define as the order. It's the smallest exponent, positive integer exponent, so that a to the k is congruent to 1. Okay? And we call it by this notation, order sub n. So it makes sense. What is the order?
Yes.
Yeah, so let's do an example. So let's take maybe mod 7 and I'll take 2. So mod 7, so it's nice, it's an odd prime, and then a is 2. So it means we write down the powers of 2, and we see the first one that is congruent to 1, right? So what are the powers of 2? They will be like, okay, we'll write them like this. So the 0th power is 1, and then we have 2, and then we have 4. And then what? After 4, we double, we get 8, and 8 is just again 1, right? So in this case, it's the 0, 1, 2, 3. It's the third term, so it means that order sub 7 of 2 is 3. Okay, so it's the... And you'll notice it's actually not the same as phi of n. So what is phi of n in this case? It's well, it's prime, so it's just n minus 1, and it's 6. So it's not 6. It's not 6, it's actually less, it's 3. Okay. Yeah, so great. So let's prove some things about order. So let's look at the first one. So the first one says that if I have Yeah, so it's A and N, and then K is what I'm calling the order. So if I have exponents X and Y, so X and Y are exponents, I want to show that A to the X and A to the Y are equal if and only if X and Y are equal mod K, right? So another way of writing this is that A to the X is congruent to A to the Y mod N if and only if X and Y are equal mod the order. Okay. So if I were to look at this sequence of powers of 2, basically it's just gonna be a periodic sequence that repeats every 3. Okay. So you guys understand the statement of this first property?
Yep.
Okay. So okay, why is it true? Oh, okay. Maybe I'll first start with this. Why does the order even exist? I skipped problem 2. Why do we even have an order? Oh, okay. It's obvious, right?
We can take
It follows from
number because
it
it's
follows
different
from
from
what
0
yours.
to 1.
What?
Yeah, we can do it using the pigeonhole principle as well.
Yeah,
Oh,
but
yeah,
actually, I
we
just
spoke about
realized
that.
it follows from Euler's theorem, right? Yeah. So actually, I'm saying something ridiculous. Okay, so let's prove the first property. Why is this true? A to the X is congruent to A to the Y mod N if and only if X is congruent to Y mod K.
Because A to the K is congruent to 1 mod N. So we just
Yes.
keep basically take it like it's remainder. So we just keep so we take A to the K times A to the KQ, and then we're just left with the remainder, and they're all unique.
So how do we know you're unique? So this is my concern, right? So I take A to the 1 through A to the K, okay, and this last one is congruent to 1 mod N. But now, how do I know these are all different? Like it could be that 2 of them are the same, right? I could have A squared and A to the. You see the problem? Like I don't know why are these all different is my concern.
Because the minimality of K.
Yeah.
So how do I use the minimality of K to show that these are all different? So suppose I need space, right? So let's create some space. Suppose, okay, maybe I erase what's here. So I have the order, so I have A to the 1 through A to the K. Now suppose X and Y are less than or equal to K and between, let's say, 1 and K. And suppose A to the X is congruent to A to the Y mod N. I need to show that X and Y are the same, right? How do I do this?
But what we should prove this for X and Y between 1 and K. What should that we prove the general case?
So then for the general case, it's this argument that Abdullah gave that it repeats, right? Like we know we have the sequence of powers, right? We know it repeats every K. Okay. So the only thing that could go wrong is if there are in this, period, in this one period, if there are repeated terms. Does it make sense?
Yes.
Like I know A to the K plus 1 is the same as A to the 1. Like I know, so like the only way this property can fail is if in one period there's repeated terms. So I want to show that's not possible. And like you said, it follows from the minimality of K, but how? I need to prove it.
Because if we have X is not congruent to Y mod K, then we have X minus Y is congruent is congruent to M for some M, and M is not 0, and so X minus Y equal K times like A. I mean L for some integer L plus M. and then 8x minus x is congruent to a congruent to 1, since a to the y is co-prime to n.
Okay, so you're
And
considering okay, so you're considering x minus y, right? Let me
yes,
make a suggestion. Let me make a suggestion because okay. Let's say let's assume y is less than x, like this. Okay. Because otherwise, x minus y could be negative, and I mean, in our definition, we didn't say anything about. Yeah, in our definition, we just said it's the minimum over positive integers, right? So, okay. So now we have a to the x. Okay, so now here's one thing we can do. Because a is coprime, a to the y is also coprime down. We just, right? It's this property that we can multiply coprime numbers. Because of that, it has a multiplicative inverse. Okay, so we can take a to the x.
or we can do that by lemma 0.
By what can we do by lemma 0? Okay, yes, you're right. You can do it by lemma 0. We're saying we can also just write it as a to the x minus y times a to the y is congruent to 1 times a to the y mod n, like this. Okay, and then you're right. Now we can do cancellation using lemma 0. And lemma 0 tells us a to the x minus y is congruent to 1 mod n. Okay, and then we get a contradiction, right? Because now it's a contradiction because it's a contradiction
x minus y is.
That's right. So x minus y is less than k, right? So and more than 0. And then we get a contradiction with the minimality. Yeah. At least, can you guys still hear me?
Yeah.
Okay, good. Yeah. So I want to point out it's very important here that we needed a to be coprime. Otherwise, this argument will fail. Right? Like, where did we use that a is coprime? In this step, when we canceled a to the y from both sides. When we used lemma 0. And you can see if a is not coprime to n, this entire thing is false. Because why? Let's take an example. Let's take mod 6. Okay, and now let's take powers of 2. Okay, so we have 2, 4, and then 8, which is maybe I picked a bad example. Maybe it's okay, right? Okay, let's not use that. Let's use let's do mod 12. Okay, let's take mod 12. So what are the powers of 2? They go 2, 4, 8, and then what's after 8? It's 16, right? And 16 is again 4. So there's 2, 4, 8, 4, 8, 4, 8. So you see it's weird. It repeats, but there's this 2 in front. That's not part of the pattern. So what happens when a is coprime to n, the pattern is perfect. Like there's nothing weird in the beginning. And it's because we have this cancellation property. Does it make sense what I'm saying?
Mm-hmm.
Okay, so great. So we proved property 1. And maybe I'll say something here, which is important. These x and y, these exponents don't have to be positive integers. They can be any integer, right? Because yeah, so I have a to the 1, 8 squared, and so on like this. I also have a to the 0, which is just 1. I also have a to the minus 1. This is the multiplicative inverse. I also have a to the minus 2, which is the square of the multiplicative inverse, and so on. So it goes in both directions. And this thing is true. This property 1 is true in all directions. Like the sequence is periodic, and it's perfectly periodic. There's no repeats in the first K. Does it make sense what I'm saying?
Yeah.
Okay, and again, that's not true for when A is not coprimed n. Right? Okay, so now let's talk about property 2. So property 2 is that this order K is a factor of phi of n. Why is that true?
Well, because one the pattern repeats every K.
Yeah, the pattern repeats every K, and it repeats by phi n as well, right? The period is K, and it also repeats every phi of n, so K divides phi of n. But okay, if we want to be formal, we can say this. We can say A to the phi of n is congruent to 1, which is A to the 0 mod n. So property 1 tells us that K divides phi of n minus 0. Okay. Okay, so now what about property 3? Suppose n is prime, so maybe it's P. Okay, and yeah, so property 3 is saying that if n is prime, so it's P, let's say, then 1 plus A plus all the way to the A to the K minus 1 is congruent to 0 mod P. So what are these? These are like all the different powers of A modulo P, because after that it starts to repeat.
But A here could not be 1.
A cannot be 1. Because you're saying if A is 1, you're right. A is 1, then it doesn't make sense, because then K is also 1 and K minus 1 is 0. Yeah, so you're right. I should add that condition, right? So you're right. So I need K not equal to 1. It doesn't make sense if K is 1. Okay, thank you. I didn't realize this. Okay.
And why we should have n is prime? I think it will work if n is not prime.
Okay, so let's prove it, and let's see if the proof works when n is not prime. So how do we prove it?
Here I mean A is not 1, not K is not 1.
Sorry, say again, I didn't understand. But no. A is 1 and K is 1 are the same thing.
Oh, yes.
You see? Yeah, A is 1 and K is 1 are the same condition.
Yes.
Yeah. Okay, so let's prove it, and let's see if it works when n is prime. So how do we prove it?
Since we have a to the K 1 mod n, and so a to the K minus 1 is congruent to 0 mod n. And then we vector.
Sorry. Okay, great. So you're saying I should use this identity, right? A to the K minus 1 is congruent to like this, right? Is equal to A minus 1 times 1 plus plus A to the K. Okay, let me just, okay, so we start with, and I wish I put more space, but okay, so we start with A to the K minus 1 is congruent to 0 mod B, or mod n, let's say. And then we factor, and so we factor the left-hand side as A minus 1 times 1 plus all the way to A to the K minus 1 is congruent to 0 mod n. But now what?
Actually, I'm wrong. N must have to be prime because we want to use the prime property.
Exactly, right. So now we want to say n divides one of these two, but we can only say that if n is prime. right? So we need n being prime here. And now, because it's prime, it tells us p divides one of the two factors. And it cannot define the first factor because of this assumption that you pointed out, I forgot to say. Because a is not 1, p doesn't divide the first factor, and therefore it divides the second factor. So yeah, the proof makes sense. So thank you for pointing out. I didn't realize, I forgot to say you need a not equal to 1. Okay, and now let's look at the fourth property. Why is the fourth property true? Yeah, so it's for general n again. If a to the x and a to the y are both 1 mod n, then a to the GCD is 1 mod n. But okay, I think it just follows from property 2, right? I think it's property 2. Right? It tells you that k divides x and k divides y, so k divides the GCD, right? It's okay. I won't write it, but it makes sense, right? It's a direct consequence of property 2.
We can
No,
also prove it
sorry, not
in other.
property 1. Sorry, yes.
Yeah, we can prove it in another way using Bezout identity.
Okay, great. Yeah. So let me. I said enough confusing things that we should just do this, right? So this is the fourth property. So it follows from property 1 is what I meant to say. So the first proof is that, okay, we have a to the x is congruent to a to the y is congruent to a to the 0. So it means k divides x and k divides y, which means that k divides GCD x comma y, which means that a to the GCD of x comma y is 1. Okay. And the second proof you were saying is to use Bezout. Okay, maybe I won't write it down, but let me just point out something, Karam. Where are we using Bezout? We're using Bezout in this implication. If k divides x and k divides y, then k divides the GCD. That's exactly why we need Bezout's lemma, right? So you have a proof with Bezout, and I don't have space to write it, but do you understand how it's exactly this implication?
Yes.
Okay, so that's what I'll say about that. Okay, great. So let's do some problems now.
Actually, I
so any
think this implication that k divides x and k divides y implies k divides the GCD of
Yes.
x and y from identity. I'm not sure if this implication implies the Bezout in the identity.
So yeah, I don't think it implies Bezout, but it follows from Bezout, like you said. And in fact, it's the fundamental reason we have Bezout. Okay. It's the point of Bezout's identity is to prove something like this. Yeah. So guys, I'm not explaining more about what Bezout's identity is because it's kind of a different topic and it's kind of to explain is kind of we need some theory to explain what the point of it is. But yeah. Okay, so let's go to let's solve some problems. So the first problem is that we have integers a and p, where p is an odd prime, and a is coprime to p. Show what? So we want to show that there exists k such that a to the k is congruent to -1 mod p. So what it means -1 is a power of a, if and only if the order is even. Okay.
So we have that a to the 2k is divisible by the order. However, 8 2k plus 1, a to the power of 2. Like, when k is multiplied by an even number, so we have 2bk. Yeah, for
Okay,
every
so
even
let's set
number,
three.
like
So
2bk,
let me start by.
Hmm.
So Adam, first let me write down. So the first thing we said is we should start with this identity. So I guess what are we showing? We're showing that if we have a solution, we're showing the forward direction. So we're showing what we are doing. We're showing that if there is a solution, if -1 is the power of p, then the order is even. And so you're saying first we start with a to the k equals -1. We square it, you get a to the 2k equals 1. And you're saying that tells us what? It tells us that
a to the 2bk is congruent to 1 mod p. I show that E strictly divides even numbers but does not divide odd numbers, so E has to be even.
yeah. Yes, you're saying ord p. So the order, we should give it a name or so. I called it k. That's unfortunate, but okay. So the order divides 2k. Okay, great. And now you're saying what?
We can build on this, like A to the 2bk, as long as if we multiply by an even number, then the order divides that number. However, we also have that A to the 3k. A to the 3k is the congruent to -1, so the order does not divide A to the 3k.
Okay. In fact, we don't need 3. We can just say a to the k is -1, right? So we can even drop the 3. We can say the order does not divide k.
Yeah, so you end up with the order does not divide k, but it divides 2k, so E has to be even.
Great, excellent. So yeah, so this is the key thing. So let's take a to the k. So yeah, this is what we have. And so again, by our properties, it means that the order does not divide k, right? So these are the two the two things we get from the properties of order. And now, Adham, you're telling us that from these properties that the order does not divides 2k but does not divide k, we can deduce that the order is even. Okay, and yeah, so is it
Because
true?
we either have that the order is 2 or that it's 2 multiplied by a factor of k, which is also an even number.
Yeah, so great. So yeah, so maybe this is right. So don't divide k, it divides 2k, so it implies it's even. Yeah, why does it imply it's even?
Because we need to have that E divides either 2 or E divides 2 multiplied by a prime factor of k.
No, it doesn't have to be 2 multiplied by let's call it v. I'm kind of okay, or not, maybe let's call it d. Let's call it d. Okay, so let's call this number d. So we have d divides 2k and d does not divide k. So it should be clear, but I'm just why does it show d as even? So d is odd. Here's what it says. Okay, so if d is odd and d divides 2k, because d is coprime to 2, then d divides k, right? So here, yeah, so right, it's this thing, right? So if we have this and d was odd, it would have no common factors with 2, so it would imply that d divides k, and we would get a contradiction. Therefore, d is even. Yeah. Okay. The argument, it makes sense.
where did we use the fact that B is a prime?
Where did we use that? P is prime. That's a good question. Maybe we did not. Okay, so if we just had yes, you're saying if I say if I just have n and I assume a and n are coprime, right? Is it still true? I think you're right. It's still true, at least this direction, it's true that if a to the k is -1, then a to the 2k equals 1. So the order divides 2k and not k. Yeah, so far we have not used that p is prime. You're correct. So far we have just, so it's a good point. So far it could have just been n and a is coprime to n. It's a good observation. I didn't realize. So let's do the second part, like the reverse implication, and see if we use p as prime. So now let's look at the reverse implication. Now you want to show that if the order is even, then there's a power that's -1. Okay, so how do we do this? So assume the order, we called it D, right? So assume D is even. Now what?
K over 2 is integer. And
Yeah, right. So D over 2, right?
D over 2, I mean here.
Yes. And what do you do with D over 2?
We have 8 to D over 2 squared
Yes.
is congruent to 1.
Right, so D over 2 is an integer. So a to the D over 2 squared is congruent to 1 mod p. Okay, so what do you do with this?
And so we have 8 to the D over 2.
A to the D over 2 is either, so
1
here's
or
where we,
minus 1.
and this is where we use that p is prime.
The minimality.
Yes.
The-
Yeah, so it's okay. So there's two things, right? So in the next step, we'll use the minimality of D, but in this step, like this implication,
prime.
we are using here that p is prime.
Yeah.
Because it's what we did before, right? We factor x squared equals 1, that's x minus 1 times x plus 1, and then we use the prime property. So in this case, we really need p is prime. Okay, so p is prime. It's this thing we talked about before, about x squared equals 1. And now, Abdullah, you were saying that now I use the minimality, right? By the minimality of D, and because D over 2 is an integer, it follows that, yeah, so by minimality of D, a to the D over 2 is not congruent to 1 mod p, and so therefore a to the D over 2 is congruent to -1 mod p. Does it make sense? Yeah, so Karam, you're right. In the previous step, in for this direction, we don't need p is prime, but in this step, we really do need p is prime. I cannot come up with an example off the top of my head when p is not prime, but you can come up with one. Okay, so any questions? Okay, so she wrote not equal. Okay. So let's continue. You guys understood the
Yes.
good. Okay, so let's continue. Okay, so here we have a problem. N is a positive integer, and you want to show that all prime divisors of 2 to the power of 2 to the n plus 1 are congruent to 1 modulo 2n plus 2 to the n plus 1. Okay. So how do we do this?
My contradiction.
Contradiction. Okay. So what if we... Okay, so maybe we can start with...
We just assume that 2 to the n is not congruent to plus 1 is not congruent to 1 modulo 2n plus 1. We did that 2 to the n is not congruent to 0 modulo 2n plus 1. However, 2 to the n is bigger than n plus 1 for all positive integers. So there must exist a number such that b multiplied by 2 to the n plus 1 is equal to 2 to the n.
Okay, so we start by assuming for contradiction that we have prime p. So assume for contradiction, there is prime p such that 2 to the... Sorry, such that...
Oh, it's all prime divisors. I thought we were just proving it for 2 to n plus 1. I did not see the prime divisor.
Yeah. So it's not that we want to show that that number is congruent to 1 mod 2 to the n plus 1. It's we want to show that the prime divisors are congruent to 1 mod 2 to the n plus 1. So okay, I see. So it's a little bit stronger actually. Yeah, so let's see. So we can start. So suppose P is a prime divisor. Okay, so it means that 2 to the 2 to the n is congruent to minus 1 mod P. Right? And now we want to conclude that P is 1 mod 2 to the n plus 1. So what can we do?
We have 2 to the n plus 1 is congruent to 1 mod b.
Yes? What does it tell us? So yes, so what does this tell us? It tells us
And now we know that the order of
we should consider the order of something, but the order of what?
The
modulo what?
order of 2 modulo p.
Right, so the order of 2 modulo p, what do we know about this?
It divides 2 to the power of n plus 1.
It divides to the n plus 1. Actually, we know more. So that's a direct. So this one directly gives us this, right? So from this statement, using the properties of order, we get this. The order divides 2 to the n plus 1. But okay, so if something divides 2 to the n plus 1, what do we know about it?
It's the power of 2 itself.
Yeah, we know it's a power of 2, right? Can we pin down exactly which power of 2 it is?
Isn't it any power of 2 that's less than n plus 1?
No, so it's not going to. If it was a power of 2 less than 2 to the n plus 1, could this be true?
No, because then it would have to be 1, not minus 1.
Yeah, so here's what's going on, right? So this statement is telling us what? It's telling us that the order divides to the n plus 1. What is this statement telling us?
So we know that the order of 2 modulo p is equal to 2 to the power of n plus 1.
But yeah, so that's the conclusion, but why?
Because if it were less, then we can raise it to some power and get 2 to the power of n is equivalent is congruent to 1 modulo p and not minus 1.
All right, so you're saying if I had 2 to the power of 2 to the k is congruent to 1 mod p for k less than n plus 1, then it would imply that 2 to the 2 to the n is congruent to 1.
Yeah, just raise it to the power
Right.
to 2 to the n minus k.
Yeah, something like 2 to the n minus
k.
yeah,
Yes.
yeah, exactly.
And it's even, so or it's yeah, you could get 1.
Yeah, exactly, right. So the problem is if the order was lower, it would be that okay, it would be 2 to the k for some k less than n plus 1. Then I can raise to some power until I get this. Okay, maybe a slightly simpler way of saying it is just okay. This guy told us that the order divides to the n plus 1. This guy told us that the order does not divide to the n. Right? Because I took the 2 to the n power, I didn't get 1. So the order divides to the n and not to the, sorry, the order divides to the n plus 1, but not to the n. Okay, and so together they just tell us that the order is exactly 2 to the n plus 1. Does it make sense?
Yeah, and since the order divides p minus 1, we get the result to be 1.
Yeah, so now the result just follows it. So now there's maybe nothing else to do. It's just okay. Now what? So from here, yeah, so now we know the order will divide p minus 1, but the order is exactly 2 to the n plus 1. And so we're done. P is congruent to 1, 2 to the n plus 1. So, yes, it's a very nice problem. It's a very direct application of order.
We can do it in another way without
Okay.
using orders.
Okay, explain.
We can, from the fact that 2 to the n is congruent to minus 1 mod p.
Yes.
I was like, no, originally, it depends. Like, originally, I proved that 2 to the n plus 1 is congruent to 1 modular 2 to the n plus 1.
Yes.
Like, if I can just put that as a lemma. We can remove the ones. Let's have it modular. No, it's modular 0. Because you have plus
Modular
1
what?
on both. It's modular 0 because you have plus 1 on both sides. So like you remove that.
Okay, so we started with 2 to the 2 to the n.
This is congruent to 0 mod 2 to n plus 1.
Yes.
I originally proved this. If we were to put it as a lemma,
Yes.
then we can write 2 to the n as ap minus 1. Then we put that ap minus 1 is congruent to 0 mod 2 to the n plus 1. We add plus 1 on both sides.
The 2 to the 2 to the n plus is congruent to, sorry, is congruent to what? AP minus, but just say again, AP minus, I didn't understand.
From the one next to it, we can 2 to the n is equal to ap minus 1.
Yes.
So we can just substitute and we'd end up with P is congruent to 1.
What about the how do from here we have this equal to AP minus 1, and then what do we do? We say AP is congruent to 1 mod 2 to the n plus 1. Yes? It's true, but it doesn't tell us that P is congruent to 1 mod 2 to the n plus 1. Do you see?
Yeah.
Right, so it's a very, very strong, yes, Khan?
maybe we use the fact that 2 to the b minus 1 is congruent to 1 mod b. And so 2 to the GCD of 2 to the n plus 1 and b minus 1 is congruent to 1 mod b. And so the order divide the GCD. But the GCD of 2 to the n plus 1 and b minus 1 must be in the form 2 to the m for some integer m. And so the order must be also 2 to the k, like 2 to the k for some integer k. And but if we suppose that 2 to the order is not equal to 2 to the n plus 1, so we have two cases. K is less than n plus 1, or k is bigger than n plus 1. But if k is less than n plus 1, then we have that implies that 2 to the 2 or 2 to the 2 to the n is congruent to 1 would be.
Yes.
And that is a contradiction.
Yes.
But the second case, I'm not sure on the second case.
Yeah, so I think what happened is, Karam, your connection, you lost maybe connection for a little bit. So you're explaining the solution that we talked about. So, but it's good. So you basically have proved that the order of 2 modulo p is exactly 2 to the n plus 1, right? This is what you've proved.
I proved the case when k is less than n plus 1. It gives us a contradiction. But what about if k is bigger than 2 to the n plus 1?
Well, first of all, it cannot be bigger than 2 to the n plus 1. It can be, it's because look, the order divides 2 to the n plus 1.
Yes.
Right.
Yeah.
So okay, maybe I can summarize your argument. So the order divides 2 to the n plus 1 like this, and because of this, the order does not divide 2 to the n. That's what this is saying.
Yeah, and the order must be in the form 2 to the m for some m.
Exactly. So it shows that it's exactly 2 to the n plus 1. But then you are done, right? Because once you know the order is exactly 2 to the n plus 1,
So,
you know 2 to the n plus 1 divides p minus 1.
Yeah, so what I have used that the order divide the GCD of 2 to the n plus 1 and b minus 1 is useless actually.
Well, yeah, I mean, yeah, but yeah, the main point is that you can figure out what the order is, right? Then once you know what the order is,
Yes.
then you're finished, right? Because it divides p minus
Yes.
1. Okay. Yeah, so I think this is a very nice problem. It shows sort of exactly how you use order in because the conclusion is very strong, right? Let's think about what it's saying. I have some number here. Yeah, I know the number is 1 mod 2 to the n plus 1 that you can show, but all of its prime divisors are 1 mod 2 to the n plus 1. That's a very strong statement. It's kind of hard to get at that without some kind of technology, right? Like if I give you a number, how can you show something about its prime divisors? It's kind of, I don't know, it's hard. But when we use the properties of order, you can say something. Okay, anyway, so let's go to the next problem. Okay, so here, what are we doing? Oh, there's a typo. I hope you guys understand. So, okay, what we want to show is that the order of 2 modulo 3 to the power of d is exactly phi of 3 to the d. So, yeah, so 2 is co-prime to 3 to the d, so it's okay. This makes sense. And so remember, it's always true that the order will divide the totient function, but we want to show that it's actually equal in this case. So the order is as big as possible for 2 and modulo 3 to the d. Great. So yeah, so I guess part A was to check that this is true. So do you guys see why this is true? The totient of 3 to the d is 3 to the d minus 3 to the d minus 1. Right, so what it means, we take 0, 1, all the way to 3 to the d minus 1. These are all the residues. Which ones do I throw out? I throw out the ones that are 3, 6, all the way to 3 to the d minus 3. So how many things do I have? There's 3 to the d things here, and I throw out 1/3 of them. Okay, and so the result is 3 to the d minus 3 to the d minus 1. Okay, so it makes sense, the calculation of the totient.
Yeah.
Okay. Okay, so now how do we show that the order, so that was how you calculate the totient, kind of standard calculation. But now how do we show that the order of this is exactly 3 to the d minus 3 to the d minus 1? So okay, let's check some cases. Let's check d equals 1 first. So in this case, I want the order of 2 mod 3. I want it to be that it is 2.
2.
Okay. And it's true because I take, what are the powers? I have 1, 2, and then 4, which is 1. Okay, so it just repeats every 2. Okay, let's take d equals 2 just to make sure we understand. Order of 2 modulo 9. What this is. So this is, we want it to be 6, right? And how does this go? That's right. So we have 1, then 2, and then 4, and then 8. And then we have 16. And what is 16 modulo 9? We can reduce it to 7. And then 7 times 2 is 14. 14 we can reduce to 5. And then 5 times 2 is 10, which you can reduce to 1. So it repeats. And so again, we see 1, 2, 3, 4, 5, 6. Okay, so the order is 6. And okay, maybe we can see the pattern, right? So for d equals 3, we want the order mod 27 to be 18. Okay. So great. So we want to show the order multiplies by 3 every time. So how can we do this?
By the way, in the question, you have that show that the order of 3 to the power of 2 and all.
Yeah, I noticed it.
the-
There's a mistake. Yeah.
Mm.
Yeah, sorry, I didn't listen to mistake. So we want to show when we increase the exponent of the modulus by 1, we are increasing the order by a factor of 3, the prime. So any ideas how we can
Would the induction work?
Yeah, so we want to use induction. Okay, since we're going to do induction, I think if we understand this one, we'll understand the general case, right? So this one is too big to do by hand. I don't know the first 18 parts of 2, it's too much. So how can we prove this? How can we find the order of 2 modulo 27? Okay, so for example, one thing we know is that the order, whatever it is, it should divide 18, right? It's because that's what the totient is. It's 18. So certainly it's a factor of 18. Can we say anything more?
Can't we just use lifting the exponent theorem?
Okay, so let's say I don't know lifting the exponent. I think I want to in the homework, one of the problems is to prove lifting the exponent. So let's say I don't know lifting the exponent. How can I understand
Okay.
this? Like what I'm trying to explain is how to go from mod p to the k to mod p to the k plus 1. It's a very important I don't know, like thing to understand.
The order must be a multiple of 6.
Okay, so why is it a multiple of 6? So you're claiming why it's a multiple of 6, but why?
Because 2 to the order of to this number is congruent to 1 mod 27, and so it will be congruent to 1 mod 9 as well.
Great. Great. So let's call this number x, for example. So you're saying 2 to the x is congruent to 1 mod 27, which implies that it's congruent to 1 mod 9. And because of this, right, because it's also congruent to 1 mod 9, because of the previous calculation, so here we're doing the inductive step, or the inductive hypothesis, it implies that 6 divides x, right? 6 was the previous order. Okay, great. So we know the order, it's divisible by 6, and it's a factor of 18. So there's only 2 things it can be. Either 6 or 18, right? So there's only thing it can be.
But why could not it be 12?
12 is not a factor of 18.
Oh, yes.
Yes. So you see, the point is I've sandwiched between 2 numbers that differ by a factor of 3. They differ by a prime. So it's one of the 2.
And now if we suppose that if it's a 6, then we have I'm not sure.
Yeah, okay, so you want to show that it's not 6, right? You want to show that it's not 6, and what does it mean to show that it's not 6? I mean, it means this. It means so let me write something. The whole point is what? We want to so we want to show we want to show that the order is not 6. That's all we need to do. And what does it mean to show the order is not 6? Well, it means I want to show 2 to the 6 is not congruent to 1 mod 27. Okay, I mean, in this case, you can check. It's what? 64 is not congruent to 1 mod 27. Okay. Okay, this one you can check, but Okay, you
But we
basically how
can't,
this shows that. Yes.
yes, but we can't check in the general case.
Yeah. So let's
The
do the. I
induction
think
case.
now. Yeah. Let's time. I think it's time to do the general case. I think we need to do the general case. So let's do that. So let's. What is the general argument? The general argument goes like this. Let's write it down. So suppose. Okay. So suppose we know the order 3 to the d minus 1 of 2 is 3 to the d minus 1 minus 3 to the d minus 2. And now we want to show that the order of this mod 3 to the d is 3 to the d minus 3 to the d minus 1. So by the same argument that we just gave, we know that whatever this order is, it's a factor of the totient function, and it's divisible by the order of the previous one, right? It's going to be divisible by 3 to the d minus 1 minus 3 to the d minus 2 by this reduction argument you gave. This makes sense, yeah?
Yes.
So, okay, and so now what's the point? The point is these two things, what is the difference? They're just a factor of 3 apart. 3 is prime. So it tells us that the order is 3 to the d minus 3 to the d minus 1. What do you want? Or it's this other thing. So now we want to show that the order is not the other one. It's not, what is it? Like it's not the previous order. We want to show that it actually got bigger. Okay, so how do we show this? So what we want is we want to show that 2 to the power of 3 to the d minus 1 minus 3 to the d minus 2 is not congruent to 1 mod 3 to the d. We want to show, we want to show that this is true. How can we do this? So you understand that we've reduced the problem to this thing, yeah?
We can just take the factor and it's even, and then we get that 2 to the power of 3 to the d minus 2 squared is not equal to 1.
So you're saying you want to write it as the following. So you want to write it as so duplicate. Okay, so you want to write it like this. Yeah, okay, so this is equivalent to 2 to the 2 times 3 to the d minus 2, not congruent to 1, mod 3 to the d. Okay. Yeah, actually, from the beginning, I probably should have wrote, this is kind of confusing. I probably should have wrote this from the very beginning. But okay. Yeah. But how can we prove this? This is not easy because we want to show that something is not 1, right?
That is equivalent to 2 to the 3 to the d minus 2 is not congruent to minus 1 mod 3 to the d.
You're saying it's equivalent to showing 2 to the 3 the d minus 1 or minus 2
minus 2.
is not congruent to 1. Is that what you're saying?
minus 1.
Not congruent to minus 1. No, because it can be congruent to 1, right?
But if it's congruent to 1, that we found a smaller order, no?
Yeah, okay. So right. So let's yeah, so the point is it's equivalent to showing it's not equivalent to, well, okay, let's be a little bit careful.
But 3 to the
Again,
d
we're
is not prime, right? Does this
yeah, so again we're solving this x squared is congruent to 1, right? So I don't know.
Yeah, I know. But we know that by the induction hypothesis that tangent of 3 to the d minus 1 divides the order of 3 to the d for 2. So and that implies that if we suppose that 2 to the 3 to the d minus 2 is congruent to 1 mod 3 to the d, then we have tangent of 3 to the d minus 1 divides 3 to the d minus 2.
Okay. Let's write like this. So okay, you're saying, let's factor it. You're saying we have 2 to the 3 to the d minus 2 minus 1 times 2 to the 3 to the d minus 2 plus 1 is not congruent to 0. And now you're saying what? You're saying I'm going to say the 2 is in the wrong spot. You're saying so we should write this, right? And then
yes.
you're saying, but now you're saying something about this factor, right? You're saying you're using the inductive hypothesis to analyze this factor.
No, actually, the induction hypothesis tells us that that the order of 3 to the d for 2 equal 3 tangent of 3 to the d minus 1 or 3 times the tangent of 3 to the d minus 1. And what we are doing now is we want to prove that tangent 3 to the d minus 1 is not the order of 3 to the d 3 to the d to the 2 to 2
Yes.
or 2.
Great. Yeah. So let me actually write what you said. I think it's a very good summary. So right. So we know that the order of 3 to the d of this is equal to either this or 3 times it. And now we want to show that they're not equal, right? Right, so this is what we're trying to do. And but what I don't understand is how we can use that to analyze this.
We use the induction hypothesis that this is actually tangent of 3 to the d minus 1.
But tangent of yes, but you see, what will that tell us? What the tangent? I mean, okay, this isn't exactly the tangent. The tangent is this, right? So this one is the tangent, but the inductive hypothesis tells us that. What will the inductive hypothesis tell us? It tells us that this thing here, it'll tell us that 2 to the 2 times 3 to the d minus 2 is congruent to 1 mod 3 to the d minus 1. It won't help us understand
Yes.
that it's not directly this, right? Like it's kind of the inductive hypothesis is giving us kind of
But so if one of the expressions is divisible by 3, isn't the other not divisible by 3?
I see. Yes.
So
So
can
you're
we
right.
use
You're,
this?
you're,
So
yes,
then
you
this
can, right?
works.
So yeah, you're right. So okay, it's a good point. So you're saying that not both of these can be divisible by 3, only one, right? Because the difference is not a multiple of 3. So it tells us that actually you can solve x squared equals 1 mod 3 to the d and get x is plus or minus 1. So you're right. So because these differ by not a multiple of 3, they can't both be a multiple of 3. So it tells us that either this is true if and only if. So that it means you want to show that 2 to the 3 the d minus 2 is not 1 or minus 1 mod 3 to the d. Okay, yeah, you're right. Okay. But I still don't see how. Yeah, okay, so
We can use that 2 to the power of an odd number is gonna be a specific modulo under 3. So only one of them, like we know exactly which one is the one divisible by 3, no?
I see. So
Uh,
okay, I think I'm getting a little bit confused. Let's do the following. Let's yes, yes.
Can we try using induction differently? We can
Okay.
just try to prove that 3 to the power of k completely divides 2 to the power of 3. Yeah, we're trying to just prove that it completely divides it. So
Yeah, okay.
um,
So
nothing
this
much.
is a good point, Karim. So let me explain Karim's comment. So I think yeah, what you're realizing is that we need something a little bit more. I don't think it's going to work if we do it just like this. So what is Karim's comment? So okay, we're trying to do induction, and you see, this is kind of it's hard to prove something like this by induction. What we do is we just
and
prove yes.
it's, we have concluded that 2 to the 3 to the d minus 2 is equivalent to minus 1 mod 3 to the d. Can this gives us like contradict the induction hypothesis?
So you're saying we assume 2 to the 3 to the d minus 2 is congruent to 1 or something? And
And could this contradict the induction hypothesis?
Can't we just prove that it's bigger than the order of 3d minus 1?
well, we don't know. We need to. That's what we need to prove, right? And it's not obvious. That's the
But,
whole thing. It's
but
not
can't,
obvious that it's bigger.
but can't we show that through the Euler function? Can't we show the now, assuming that the order is equal to the phi function for d, we know that the phi function of d plus 1 is 3 multiplied by that.
We don't know that.
So,
That's what we need to prove.
okay,
We know that when we go from 3 to the d to 3 to the d plus 1, the order function either stays the same or multiplies by 3. We don't know which one. We need to show that it multiplies by 3.
no, I'm not talking about the order function. I'm talking about the Euler function. We know that it gets
Yes.
multiplied by that. We know that it gets multiplied by 3,
Yes.
right?
Yeah, yes.
All right. So
That
we
we know.
know that the order of d plus 1 divides phi of the Euler function of d plus 1.
Yes.
But at the same time, the order of d plus 1 divides 3 multiplied by the order of d.
Yes.
All right, so and the order is bigger than 3. Order of d plus 1 is bigger than 3. So, oh, I got lost again.
So okay, there's a lot of numerics you can do, but at the end of the day, you need to show, like, this whole thing boils down to showing that when you go from mod 3 to the d to mod 3 to the d plus 1, the order multiplies by 3. For 2, not in general, but for 2. Like for a equals 2. It's not true in general, but okay, so here's what I'm gonna do. There's a lot of suggestions. I'm gonna try to maybe combine them into one thing. Yeah, so let's see. So let's start with what we know. So we know this. Amino acid is 2 times 3 to the d minus 2. Okay. Right. We know that the order is for d minus 1 is 2 times 3 to the d minus 2. What does it mean? It means that 2 to the power of 3 times 2 to the 2 times 3 to the d minus 2 is congruent to 1 mod 3 to the d minus 1. But it also means that 2 times no, okay, sorry, I'm confused. So this is not what we're going to do. Okay, so sorry. And now we want to show that 2 to the power of this same number, yeah, let's look like this. We want to show that this is not congruent to 1 mod 3 to the d minus 1. But you see, this should be the inductive hypothesis. What we want to really show is that, so this is what Karim was saying, is that what we really want to show, okay, so this is our claim, and we want to show this by induction, is that 3 to the d minus 1, they completely divides this number. Okay, so we want to show that 3 to the d minus 1 divides it, but 3 to the d does not. Does it make sense? This is the whole, like, crux of the argument, right? Because we know, this is the order mod 3 to the d minus 1, but we want to show that when you go to the 3 to the d, the order doesn't stay the same. So you want to show that this is true, but this is not true, which means you want to understand exactly that this is true. Does it make sense what I'm saying?
Yes.
Right. So like, when we want to do the induction, right? What we need to understand is that, yes, 2 to the totient of 3 to the d minus 1 is 1, but 2 to the totient of 3 to the d minus 1 is not 1 mod 3 to the, sorry, I wrote the wrong thing. Okay. Yeah, so this is what I want. I want this, but not this. That's what lets me do the induction. And what it means is I have to show this by induction. But this is something you can show, right? Because how do we do this? Yeah, so let's prove the claim. Okay, let me say something. So let's make sure we're all on the same page. Do you guys understand that if we have the claim, we can solve the problem? Does that make sense?
Yes.
Okay.
This claim is equivalent to 2 to the d, 3 to the d minus 1, fully divides 2 to the 3 to the d minus 2 minus 1, or 3 to the d minus 1 fully divides 2 to the 2 to the 3 to the d minus 2 plus 1, because as Abdullah says that t 2 to 2 to 3 to the d minus 2 minus 1 and plus 1, these two numbers differs by 2, so they can't be both multiples of 3.
This is right. This is right. So yeah, so it's equivalent to 3 to the d minus 1 fully divides this one or this one. And yeah, the point is, I think it's going to be this one, right? So, but okay, yes, this is true, but I don't want to go that direction. I want to go to the direction of how do we use induction here, right? So I'm going to prove this claim by induction. So understand, there's two layers of induction here. Once I have this claim, I can use induction to solve the problem. I can also prove this claim by induction. Okay, so how do I prove this claim by induction? So let's see. The way I prove this claim by induction is I say, okay, so let's move this here. Okay, so let's say I have 3 to the d minus 2 fully divides 2 to the 2 to the 3 to the d minus 3 minus 1. Okay, and now I want to understand this guy. Well, so if to understand 2 to the 2 to the 3 to the d minus 2 minus 1, the point is this exponent is triple of this exponent. So the identity I need to use to understand is x cubed minus 1 equals x minus 1 times x squared plus x plus 1, right? Because I'm going from this exponent to triple the exponent. Okay, so I should use this identity. And what does it equal? So it's the previous term minus 1 times what? Times 2 to the power of 3 to the d minus 3 squared plus, sorry. 2 times 2 to the 3 to the d minus 2 plus 2 to the 2 times 3 to the d minus 2 plus 1. Yeah, does this make sense?
Yes.
Okay, so what now? So how many factors of 3 are there here? So here, by inductive hypothesis, we have exactly 3 to the d minus 1. Okay, we could say it like this. Exactly d minus 1 factors of 3. Yes, it makes sense. Oh, no, sorry, not d minus 1. D minus 2. Sorry, d minus 2. Yes, this makes sense. There's d minus 2 of them. So what do I want to show about this?
We want to show that the 3 fully divides this expression.
Right. And now this is considerably easier because, well, it's like we're not dealing with, we can just do it mod, what is it, mod 9, right? We want to look at this mod 9. Like, what does it mean to show that this is 3 fully divides this? It means we want to know what this is mod 9. Okay. And what is it mod 9? Well, first of all, what is it mod 3? I mean, okay, can we see that this is divisible by 3? Yes, we can, because these are all 1 mod some super high power of 3, so it's 1 plus 1 plus 1, it's 0 mod 3. And how do we see that it's not divisible by 9? It's the same argument. I mean, this is 1 modulo some huge power of 3, so in particular it's 1 mod 9, right? That's what the induction hypothesis says. These are all 1 mod 9. So this whole thing is congruent to 3 mod 9. Do you guys see?
This uses induction hypothesis.
Yes, it uses induction hypothesis. What is the induction hypothesis? The induction hypothesis is that, or part of the induction hypothesis is that, well, the induction hypothesis is very strong. But in particular, it says the induction hypothesis says that this is congruent to 1 modulo, what, 3 to the d minus 2, right? So I don't have to write 9 here. In fact, I can write this is congruent to 3 mod 3 to the power of d minus 2. And in particular, also mod 9. So it means that 3 divides it and 9 does not. Does it make sense?
Yes.
So yeah, okay, so what's the idea? We wanted to compare powers of 3 in this versus this, and so we used this identity, and it gave us the relation. Okay, so does the proof of the claim make sense? This is the claim.
Yes.
Okay, so that's the claim, and okay, and yeah, and so once we know the claim, okay, yeah, once we know the claim, you can prove this statement by induction. Okay, yeah, maybe I'll leave it there. So yeah, so there are a lot of steps in this problem actually. I would recommend writing the complete solution to this problem. You can do it as as one of the 2 homeworks to submit. You can write the complete solution to this problem because there are a lot of steps, right? You have to and we can summarize, right? So first what? First we had this thing, right? So we tried to prove by induction, right? So first we say, okay, suppose we know this, we want to show this. Because we can sandwich the order mod 3 to the d like this, it reduces to showing that the order mod 3 to the d is not the same as the order mod 3 to the d minus 1, which then, if you understand what that means, it's equivalent to the claim. And the claim you prove by induction. Yeah, so yeah, I guess you can try to write down the solution for homework. Yeah, so any questions about this problem? Does anybody want me to go through the argument again, like at a high level?
Uh, as I gotta make a side note. Aside from the two homework problems, can I send you a different proof to this and ask if it's
Yeah,
correct?
of course. You can send me anything and I'll take a look and I'll let you know. And then if you want me to specifically like um give you comments about a particular problem, like the way you wrote it, tell me and I will. Like I know last week you did. You gave me some kind of specific thing. You can do that. It's completely fine. Okay, so if there's no questions, I didn't cover everything. It's okay. I guess yeah, we'll just continue next week. Um, with we'll continue next week. Maybe I'll say this for this week. What did we do? We finished the warm-up. Okay, so I guess the homework for this week can include this. Here's what I'll say about the homework. Problem 7 and 8 are basically same ideas we've been using. Problem 9 also very similar. For problem 10, you need some kind of new idea. So maybe I'll cover problem 10 next week. So this one I will do next week. But the rest of them, okay, also problem 17. This will also be next week. So yeah, so I think problem 10 is, but other than problem 10, problem 17, and maybe also problem 14. So okay, besides these three, that's besides 10, 14, and 17, all the problems are basically about order. Yeah, so okay. The homework will be everything except for 10, 14, and 17. And then we'll cover those next week. Okay, any questions before we break?